Hello and welcome to the course. In this video, we're going to initialize our program. Well, this is the first video that's about both simulation and MATLAB, therefore I'm quite happy. So let's get immediately started. Again, like I said, we're going to initialize. So this means we're going to initialize all the states that we have to further develop the simulation. I'm going to first define the simulation parameters. And by the way, as I proceed, I'm going to talk about what I'm performing. Okay, so let's get started by dt. This equals the time step we have, and recall from the earlier method, we have a little time step here, and also let me have my pen here. We will be defining this. So we will perform first the takeoff, but we didn't come to that yet. But for the takeoff, we want to examine a close time intervals, such as the rotation, which is important. So I want to keep the time step small. Therefore, I choose 0.01, which is second. Now I'm going to define the step counter as I equal to 1. We're going to start from 1. And finally, let's define our master clock, which is time. And let's get started from 0. Okay, these are my simulation parameters. Now I need aircraft data. And to do that, I have a struct data that contains all the required data for my aircraft. For example, aerodynamics, propulsion, moment, and so on. Also the geometric data of the airplane. So I'm going to call that as AC for a short definition. Then I'm going to call my struct data, that's called as T38 general data, and I have that in the path already. And this is it. Well, we're going to obtain this. This is a subject of another video. So I'm going to just initialize the program here. I'm going to mention about this struct data later. Okay. And now, time to define the initial conditions. Recall that we need those data for the x, z, u, v, theta, and q. And now we're going to define them. Let's get started by xe, which states my x position respect to the Earth. And it's the ith value, which means the first value. So we are defining the first value, which equals to 0, of course. We're going to start from 0. Okay, it's time for the z, which stands for the altitude, of course, and which also equals to 0. Now it's time for u. Now, because we're going to start from 0, we should say that u is equal to 0. But we cannot simply do that because of the angle of attack's definition. Recall that angle of attack is defined with the arctangent w divided by u. And if I make the u equal to 0, that breaks everything. That's a zero division error. So I don't want that. Therefore, I'm going to give a slight value to that. Let's say 5. And of course, this is meters per second. And recall that because w is equal to 0, the angle of attack is equal to 0, and which is correct for the takeoff. So let me define w, which stands for the velocity in the z-axis. Of course, this is for the body axis, and it's 0. And the theta, the pitch angle, is equal to, of course, 0. And finally, the pitch rate q, and this also equals to 0. Okay, we have those 6 values already, and we need one extra, that is the mass. I mentioned that mass should be decreased because we are analyzing a jet engine which burns fuel. So the first initial mass is equal to, now we have this data from our general data, so I'm going to pull that data as AC dot mass, if I can type, mass initial. Okay, this will immediately take the value that's assigned as initial inside of the struct data, and we're going to come to that. Okay, now we have the first mass data, and now we need to calculate the initial atmosphere and state. And to do that, I have a perfect function. That's a MATLAB built-in function and comes with the aerospace block set, and which is called as Atmosisa. Okay, what we're gonna get from Atmosisa? We're gonna get nothing here, because as I remember, this gives us temperature, but we don't need the temperature. I believe let's actually look at that. Let me show you the Atmosisa. What the first value gives me. Okay. Yeah, temperature, speed of sound, pressure, density. What is new? What is new? Yeah, kinematic viscosity, it's written down here. And the dynamic viscosity, mu. And we will need the A here, which means the speed of sound, and the rho, which is the density. Okay, therefore I don't need this. And let's obtain our speed of sound as the first value. And we don't need this. And let's get our density. And I don't need this too. Okay. What will be the input? The input will be the Z, which stands for the altitude, and of course the I value. However, the Z-axis here, defined as negative, because recall from the coordinate systems, the Z-axis always points to the downward, and therefore the positive side points to the downward. But for, logical ways, we're gonna say that going up is positive, and to do that, I'm gonna add a negative value to it. Throughout the calculations, that will be calculated as the flight dynamics approach. And for the visualization, let's say, and also for the Atmosisa function, we're gonna add a little minus sign here to make everything logical. Because as we increase our altitude, we need to state that, and we see changes in both density and the speed of sound. Anyways, okay. Actually, we don't need those because it's waste of place. We don't need those. Okay. Now I'm going to create a new struct data that will store the environmental data to send them into the main function. I'm going to call that as N, which stands for the environment, and I'm going to create a struct which will accept the row, which is the density, and I'm going to copy this. Similarly for A, and we're going to copy this. And finally, not finally, we have two more. We're going to define G, which is gravitational acceleration, and it is assigned as 9.81. And finally, let us have the mu, which is the friction coefficient of the ground. So let us assign as 0.04. I'm going to mention about this in the takeoff part. Okay, so don't forget the semicolon. And finally, we need to create our state struct data to, of course, send it to the main function. And to do that, I'm going to create a struct data that's called state equal to struct. And now I'm going to input first the mass, and I will copy this. And the other data. Let's get started by XE. And let's copy this. And now I can copy this. And let's change this to that. And let's do the same thing. And this term. And right now this will be U. Okay. Let's go down and paste again. And this will be W. And this will be W again. We have 2 more, which are, let's say, theta here. And this theta. And finally, we have Q. Okay. This is also packed to be sent to the main function. Okay. Now we need to initialize the controls. We have 2 controls. The first one is the elevator deflection, which is the horizontal tail deflection, but we're going to call that as elevator deflection. And the second one is the throttle setting. So I'm going to also create a struct data, and I'm going to say that control dot elevator deflection, which equals to 0, because we're going to assume that during the takeoff, the moment equilibrium is met. Therefore, I don't need to deflect the elevator, because we're going to assume that the moment is equal to 0 anyways. But we're going to assume that during the ground roll, from the rotation and the airborne, we can't simply assume that, because we need to deflect the elevator to have the pitch up moments and to pitch up actually. Anyways, for this, let's make it equal to 0. And finally, control tells me throttle setting. And we're gonna take off with full afterburner. Therefore, this equals to 0. Sorry, 1, not 0, clearly. Okay. Now, we need to have a function that calculates all the forces and have the changes here. I mean, we need a function that gives literally us, not this actually, this. And this will be the core of the simulation, and therefore this is the core of the whole course. Now we will call our core engine, our physics engine, flight dynamics. So I'm gonna first type the output, which the flight dynamics yields us. And I'm gonna call that mighty function flight dynamics, which is here. And which will accept the states that we packed, AC that we have, environment that we packed, and the controls that we have. Let me write that clearly. And this is it. I mean, this function does everything. I mean, this is a magical function. But don't you worry, we're gonna also talk about this with a separate video, because this is the most important part of the course to me. Okay. Now, let's assume that the flight dynamics did its job and we have the output. Now, I need to store the output, and I'm gonna store that as the simlab. Which is the output. This will store the data, and if I would like to use the data, this the simlog stores, I need to unpack it. We're gonna also do that. After this, we will start to perform our phases, and the first one will be the ground roll. And as you can see, the flight dynamics gives us this, and we have this already, so we're gonna have the second iteration for the next phase, which is the ground roll. But before of it, I need to talk about the takeoff. I mean, what is the takeoff? How do we perform the takeoff? But we still have time for that. But before of it, we are going to talk about first the T30 general data abstract. How do we use it? I mean, how do we obtain it? And why this is crucial for our simulation. Then the most important part, the flight dynamics function. We're going to create this flight dynamics function from scratch. And this also another video. And lastly, we're gonna code the post-processing and plotting part. I mean, we haven't talked about the main function yet, where the phases are performed, such as takeoff, climb, cruise, or whatever. But for gaining time, I will talk about the post-processing as a third video that we are going to start to the takeoff part. So thank you so much for your attending. By the way, I'm not going to share this code to you because you have nothing to do with this code. I mean, you can't run it. I mean, you can run it, though it simply doesn't help you. I mean, this is not a iterative code, let's say. I'm going to share this code with the ground roll code. I mean, once we start to type or code the ground roll phase, we're going to continue on this. Anyways, thank you for your watching and attending, and I'll catch you later.